We've all heard of Angry Birds, the popular modern video game in which birds are flung from a slingshot towards pigs. Today, we're going to debunk some myths about this game and we'll show you how these birds will fare in real life. Let's look at the flight of these birds. The birds travel in a perfect arc, traveling half of their horizontal distance before reaching the peak and the other half after the peak. Let's first see what happens in the Angry Birds game.
When the redbird is launched at an angle, the bird travels in an arc. Gravity pulls down on the bird with an acceleration of 9.8 meters per second squared. The bird at the peak of its trajectory has a speed of 0 meters per second. If we look at the Angry Bird's initial launching, there's a horizontal component and a vertical component. The angle in between is theta, and the initial velocity is x meters per second. The vertical component is x sine theta, using a magical function called trigonometry, which we'll learn later. The horizontal component is x cos theta. The horizontal velocity never changes and will stay the same throughout the entire flight. On the other hand, the vertical velocity will decrease on the way up and increase again on the way down. Now, let's find how far up the bird's peak will be using this equation. V final squared minus V initial squared equals 2AD. V final is the final velocity that you want, which is 0 meters per second in this case. V initial is the initial velocity, which is x sine theta, and A is for acceleration, which is 9.8 meters per second squared from gravity. And D is the distance from the ground to the peak. The main driver for the projectile motion is gravity. Anything that falls toward the ground is accelerated downwards by the Earth. That means on the Angry Bird's way up, the vertical velocity decreases by 9.8 meters every second, and at the top of the arc, its velocity is 0 meters, and it finally falls back down with an acceleration of 9.8 meters per second squared. Since we have the distance now, we can find the time it takes to reach the peak. We have the equation distance equals v initial time plus 1/2 at squared. D is still the distance from the peak to the ground. V initial is still x sine theta, and the acceleration is still 9.8 meters per second squared. To find the horizontal distance, we would multiply the horizontal velocity by the total time. Therefore, in the game of Angry Birds, we can find exactly where and when the bird will land. Now, if we look at all these equations, we realize that mass is not mentioned in any of them. Technically, how much a bird weighs has no effect. However, in real life, there is air resistance, and if an object weighs more, there will be more air resistance, which will be shown in the next part.
Here we have a setup of the Angry Birds, and the wind will act as a source of air resistance. Here we can see that the arc is not perfect because there is the force of air resistance pushing it back and shortening its travel distance. As we can see here, with the same force and angle, the large bird flies much less further than it would have in the game. Furthermore, we can see that the arc of the bird is not even. Because of air resistance, we cannot calculate exactly where the bird will land in real life. For this, mass plays a part in the flight of the birds. To explain this, we can look at a free body diagram. It shows all the forces acting on the bird during its flight. Here we can see that there is the force of gravity and the force of air resistance acting on the bird. Also, Newton's second law, force equals mass times acceleration, or acceleration equals force over mass, can be used. The force of the wind stays constant, let's say it is 1 Newton, the unit of force, and let the mass of the red bird be 2 kilograms. Therefore, the red bird would have a backwards acceleration of 1 Newton over 2 kilograms, which equals half times meters per second to the second. If the mass of the bird changes to 3 kilograms, the backwards acceleration would be 1 Newton per 3 kilograms equals 1 over 3 meters per second squared. So, wind resistance applies a force against the direction in which the birds are traveling, and lighter objects are more affected by it than heavier objects. So the game is in a virtual vacuum with no air resistance.
Let's take a quick recap of what we discussed today. Through kinematic equations and projectile motion, we learned how to figure out the exact location of impact. We also learned that mass does not have any effect on the projectile motion of objects in a vacuum. Finally, we learned that in real life, Angry Birds would be very different because of air resistance. So there, now you have a general understanding of Angry Birds, the game, compared to what it would be in real life. So the next time you play Angry Birds, thank the creators that they forgot to put in air resistance. Bye.